Welcome back to the third part of our series on HVAC design requirements for school construction authority projects. In the first video, we walked through the general design principles. In the second video, we focused on system applications and specialized requirements. Today, in part 3, we'll continue by covering acoustical standards, seismic design, special spaces, refrigerant leak detection, and several technical upgrade requirements. This session is designed as a concise overview, giving you the key details you need without overwhelming you. Let's get started. The standard sets maximum permissible background sound levels, measured in both dBA and NC values. For example, classrooms must not exceed 40 dBA or NC 35, while music rooms and auditoriums must be even quieter, at 30 dBA or NC 25. Spaces like cafeterias and kitchens are allowed higher levels, up to 50 to 55 dBA, because of their function and equipment use. It's important to note that these background limits only apply to continuous mechanical noise from HVAC systems. Transient sounds like traffic or aircraft are excluded from this requirement. The guideline also defines duct and terminal velocity limits, since higher airspeeds can create excessive noise at outlets. Each noise criterion level is tied to a maximum duct velocity. For instance, an NC 35 supply duct should not exceed 1,000 feet per minute, measured 30 feet upstream from the terminal. Round ducts and plenums may be allowed slightly higher velocities, but must remain within recommended ranges. Installation practices are equally important. VAV boxes and dampers must be located far enough upstream, usually 5 to 10 duct diameters, to avoid turbulence and noise at diffusers. Sound traps are required on VAV boxes, and fan-powered boxes are limited to 1200 CFM unless specifically justified. Plenums serving heat pumps or dual-temperature air handling units must be acoustically lined with double-wall construction and fiberglass insulation to contain noise. Duct lining is only permitted when silencers alone are insufficient. If fiberglass lining is used, it must comply with ASTM standards for fire resistance and fungal resistance. It must be fully sealed to prevent fibers from entering the airstream. Diffuser design is also regulated. Standard ceiling diffusers are preferred, while linear diffusers are only allowed when the heating load exceeds 250 BTUH per linear foot. This ensures that design choices are not made for appearance at the cost of noise performance. Noise and vibration isolation measures are mandatory. All equipment must be mounted on vibration isolators, with seismic restraints applied according to NYC codes. Ducts may also require spring or neoprene hangers for additional isolation, and airtight flexible fabric connectors must be used at equipment connections. Exterior mechanical equipment is subject to both the NYC Mechanical Code and the city's Noise Control Code. That means rooftop units, condensers, and outdoor fans must comply with strict noise ordinances enforced by the Department of Environmental Protection. Finally, an acoustical consultant must be engaged during design. Their role includes reviewing the need for sound traps, duct lining thickness, acoustic enclosures, and barriers around noisy equipment. They also determine whether more advanced measures, like floating slabs or special enclosures, are needed for sensitive spaces. To further reduce noise, heat pumps and rooftop equipment may require condenser fans with VFD staging, compressor jackets, insulated roof curbs, and acoustically lined outdoor air intakes. In short, Section 6.2.25 ensures that HVAC systems in NYC schools meet the high standards of acoustic comfort required for learning, by combining design limits, careful installation, noise isolation, and professional oversight. Seismic safety is an important part of HVAC design in New York City schools. The School Construction Authority requires systems to be properly braced and certified to reduce risks during an earthquake. This section is based on the 2022 NYC Building Code in ASCE 7/2016, and applies to all new schools, major additions, and retrofits. Schools are classified as Risk Category 3, meaning they are considered substantial hazard to life buildings. A key concept here is the Component Importance Factor, or IP. For most components, IP is 1.0. For life safety systems, hazardous equipment, or units near those systems, IP increases to 1.5. This higher factor requires stronger bracing and certification. All gas-fired boilers, rooftop units, and other IP equals 1.5 systems must be seismically braced. In Seismic Design Category C, ductwork also requires bracing when IP is 1.5. For alterations, the 1968 NYC Building Code with DOB interpretations applies unless a waiver is obtained. For additions, any tie-ins between existing and new systems must meet seismic standards. Bracing must use certified hardware and anchors, such as NFPA 13 approved clamps with straps, and anchors rated for cracked concrete. Bracing devices must also be tested to ICC SAC 156 standards using NYC seismic data. Not all equipment must remain functional after an earthquake, but smoke control fans and emergency systems must continue operating. That performance can be proven through engineering analysis or shake table testing. Finally, a New York licensed professional engineer must design, seal, and submit restraint calculations, supervise installation, and certify compliance with an affidavit. In short, Section 6.2.26 ensures HVAC systems in NYC schools are not only efficient, but also safe and resilient against seismic events. By setting strict codes, assigning responsibility to licensed professionals, and requiring certified equipment, the SCA ensures that critical building systems can withstand seismic events without putting students or staff at risk. Some areas in schools have very specific HVAC needs. This section covers telecom rooms, electrical and UPS rooms, elevator machine rooms, science labs, kitchens, duplicating rooms, and special education spaces. Telecom rooms must maintain 75 degrees Fahrenheit and no more than 55% relative humidity, running continuously with dedicated VRF or split systems. Temperature and humidity sensors must also be tied into the BMS or DDC for monitoring. UPS and elevator machine rooms require independent ductless systems operating around the clock. Elevator rooms must stay between 50 and 90 degrees with humidity under 95%. UPS rooms with VRLA batteries need dedicated exhaust ventilation at 1 CFM per square foot, and the system must be tied into the fire alarm for safety. Science labs are designed to stay under negative pressure, using ducted fume hoods and fan-powered VAV boxes with reheat to control air quality. Kitchen food storage areas must remain between 50 and 70 degrees, served by dedicated split systems. Duplicating rooms generate heat and odors, so they require continuous exhaust at half a CFM per square foot, with the space kept under negative pressure. Finally, special education classrooms require a stricter cooling set point of 75 degrees instead of the standard 78, ensuring better comfort for sensitive occupants. This section provides very specific HVAC design requirements for telecom, electrical, emergency, food storage, science labs, special education, duplicating rooms, cooking, and athletic facility spaces under NYC SCA standards. When A2L refrigerants are used, special precautions are required to protect occupants and staff. This section ensures that if a leak occurs, the system reacts quickly and safely. If refrigerant levels approach unsafe limits, the system must automatically shut down the compressors and trigger both audible and visual alarms. These alarms are located in the mechanical room and also connect to the fire alarm system for central monitoring. Ventilation must shift from normal operation to emergency exhaust to dilute and remove leaked refrigerant. Break glass switches, mounted outside the room, give staff a way to immediately stop compressors or activate fans if needed. Finally, all exhaust discharge points must follow NYC mechanical code clearances, keeping refrigerant away from intakes, doors, and stairs. Together, these measures ensure compliance with ASHRAE 15-2022 and NYC codes, while maintaining safety in schools that use A2L refrigerants. This section applies to capital improvement projects in schools that use steam perimeter heating with public assembly air handling units. If the project cost is $2 million or more, the design must demonstrate at least a 5% annual energy savings compared to baseline conditions. Upgrades can include demand-controlled ventilation using carbon dioxide sensors or the use of energy recovery wheels. If an energy recovery wheel is installed, demand control ventilation is not required. Retrofitted units must be equipped with DDC controllers, room sensors, and modulating actuators. Steam valve actuators must be replaced with spring return, Modulating types for reliability. Whenever possible, systems should be designed with native backnet for seamless integration with building management systems. Recirculating units and 100% outside air units are controlled by carbon dioxide sensors and VFDs. These controls optimize ventilation rates and balance energy use while maintaining indoor air quality. This section applies when condensing boilers are retrofitted or replaced in existing heating systems. The standard heating approach for new schools is heat pumps, so condensing boilers require special approval. When allowed, boilers must run on firm gas only and use linkage-less burners for safety and precision. The gas meter room must be equipped with explosion-proof fans, lighting, and switches. Gas shutoff valves must be provided both at the firm gas main and inside the gas meter room. Each boiler must have a gas leak detection system, and all valve trains must comply with ASME CSD1. Performance is also critical. Boilers must achieve at least 88% thermal efficiency at full load with 130 degrees Fahrenheit return water. To support condensing operation, piping should be balanced, reverse return preferred, and fin tube radiation designed for lower supply temperatures. Condensate from boilers must flow through neutralization tanks before draining. Exhaust must use double-wall metal vents approved for condensing boiler applications. Finally, sufficient clearances and access must be maintained for servicing. If height or access limits are an issue, special reconsideration must be filed with DOB. When hydronic lines are run outside a building, or when they serve units that bring in outside air, they need extra protection. In these cases, the lines must be filled with a 30% propylene glycol and water mix to prevent freezing. For piping that's completely indoors and not exposed to outside air, plain water is acceptable. The same 30% glycol mix is required for any project where piping runs outside the building, or when interior air handlers draw in outdoor air. Basements and crawl spaces also need to be protected. Heaters should be installed to keep those spaces from freezing. If the boilers are turned off at night, electric heaters are required. But if the boilers stay on continuously, steam or hydronic heaters can be used instead. These measures help keep the system safe and reliable during cold weather. This section ensures that air system designs are carefully reviewed and verified at key project milestones. Engineers must submit detailed calculations during the design process, at 50% for capital improvement projects, and at both 60% and 100% for capacity projects. The calculations must confirm that the system can deliver heating and cooling loads, taking into account transmission, infiltration, and ventilation demands. They must also include allowances for fan static pressure losses due to wet coils, turbulence, and dirty filters. Airflow through cooling coils must stay below 450 feet per minute to prevent condensate carryover. Engineers must also justify diversity factors used in variable volume systems, especially if they differ from the typical 85% block load assumption. Finally, every VAV box and baseboard must be shown to meet its required capacity. In special cases, such as projects with tight floor-to-floor heights using dedicated outside air systems or unit ventilators, engineers must demonstrate that latent and sensible loads are fully met. That wraps up Part 3 of our 4-part series on HVAC design requirements for SCA projects. We've now covered acoustics, seismic safety, special spaces, refrigerant leak detection, capital improvement upgrades, condensing boilers, freeze protection, and system verification. In the final video, Part 4, we'll complete this series with more technical requirements and compliance notes. Thank you for watching, and don't forget to like, subscribe, and check out the earlier parts if you haven't already.